In this video, we'll look at how compact operators interact with weak topologies, and we'll prove two propositions. One takes place in reflexive Banach spaces, and in those spaces the relationship is very neat. The compact operators are exactly those operators that improve weak convergence to strong convergence. And then we'll look at separable Banach spaces, and we'll exploit the Banach allow glue theorem to show that when a space is separable, at least we can guarantee that the adjoint of a compact operator stays compact. So let us prove these two propositions. Okay, so let's start with a compact operator on a reflexive Banach space, and let's give ourselves a sequence xn and a vector x such that xn tends to x weakly. Right. Now I want to prove that t of xn goes to t of x strongly, and I'm going to act by contradiction and assume that there exists an epsilon and there exists a subsequence such that t of x and k stays away from t of x. Epsilon away for all k. Okay, and we'll get a contradiction from that. Now, this subsequence is bounded, so t of x and k has to stay bounded because x and k is bounded, and that's because x and k converges weakly to x, so is bounded. Okay, so I have, and t is a bounded linear operator, so I have a bounded sequence, and t is, well, I have the image of a bounded sequence by t, and so I can extract the converging subsequence because t of a closed unit ball, or t of any closed ball for that matter, just by scaling, has to be compact. So because t is compact, I have that there exists a further subsequence, xnkl, such that there exists a y in x, such that t of xnkl converges to y, as L goes to infinity. Okay, but now if I converge strongly to y, then in particular I converge weakly to y, so for every x in x star, t of xnkl, comma x star has to tend to y, comma x star, as L goes to infinity. But now this means that for every x star and capital X star, xnkl, comma t star of x star, and t star is a well-defined bounded linear operator. As L goes to infinity, this has to go to y x star. Okay, for every, then that's for every x star. But now, in the meantime, I know that xnkl converges weakly to x. So I also have that xnkl, t star x star, converges to x t star x star as L goes to infinity. And that tells me that y has to be equal to t of x. And therefore, I have that txnkl minus t of x tend to 0 as L goes to infinity. But that's exactly saying that I can extract a converging subsequence from this sequence here that goes to 0, and that contradicts the fact that all of these things have to stay greater than epsilon. This contradicts t of x and kl minus t of x greater than epsilon for all L. Okay, so we have our contradiction. So this assumption here has to be false. So t of xn has to go to t of x in the norm topology. Right, so we've proven one direction. We've proven that compact operators turn weakly converging sequence to strongly converging sequence. Let's have a look at the reverse direction. So in the reverse direction, this is a little simpler. We proceed as follows. So let's give ourselves a sequence in the closure of the image of the unit ball by T, and I want to extract a converging subsequence from that sequence. So how am I gonna do that? Well, first of all, I'm gonna pick for every n in n, xn in the unit ball bx such that t of xn minus yn is smaller than epsilon. So fix an epsilon and do that. Now that I have my sequence xn, I'm going to use the Banach-Alaoglu theorem such that I can pick a subsequence and a x in x, such that x and k converges weakly to x. So that is by Banach-Alaoglu and reflexivity, which allows me to run the Banach-Alaoglu compactness argument for the weak topology. All right, so I have x and k that goes weakly to x, and now that tells me that t of x and k, x star, tends to t of x, x star, of course, because I could bring the t onto the x star and just use the weak convergence of the x and k. So of course, bounded linear operators turn weakly converging sequences to weakly converging sequences. And we're about to say that compact operators improve that to strong convergence. Okay, so I have that, and now I can use my assumption and say that because I have weak convergence of the t x and k to t of x, I have strong convergence of the t x and k to t of x. Okay, but now that means that for every epsilon, there exists a capital K in n, such that for every little k greater than this capital K, ynk minus t of x is smaller than tx and k minus ynk plus tx and k minus t of x. And by picking my k large enough, I can make this smaller than epsilon, and this is always smaller than epsilon by definition of the xn. So this entire thing is smaller than 2 epsilon. So we've found a converging subsequence from any sequence yn in the closure of the image of the unit ball by T, and therefore our T bx is compact, which is what we wanted to prove. Okay, so in reflexive Banach spaces, the compact operators are exactly those operators that turn weakly converging sequences into strongly converging sequences. All right, now to finish this little video, we'll see another Banach-Alaoglu argument. Now this time in separable Banach spaces, where we know the weak star topology is metrizable on the unit ball. We'll look at a compact operator and prove that its adjoint is also compact. So how do we do that? We take a sequence xn star in the unit ball of our dual. Okay, and now what we do is we use Banach-Alaoglu to extract a weakly converging subsequence. So there exists xn star k, and there exists x star and capital X star, such that x star and k tends to x star as k goes to infinity, and that's in the weak star sense. Okay, now when I look at t star of x star and k minus t star of x star in the norm of capital X star, well, I'm really looking at the supremum over all x in the unit ball of x of, what is it, x star and k minus x star applied to t of x. Right, but that is the supremum over all x of that is certainly smaller than the supremum over all y in not just t of b of x, but its closure of x star and k minus x star comma y. But now I'm taking a supremum over a compact set. So by a total boundedness argument, I have the fact that this convergence for every y, which is the weak star convergence, imply by compactness of the closure of the image of the unit ball that the supremum over order y in this set of these quantities has to go to 0. And this is exactly telling me that my T star, X star, and K is a converging subsequence. So this converges to T star, X star. So we found a converging subsequence on the image by T star of any element of the unit ball of X star, and you can go to the closure exactly like we did in the proof of proposition 12.6, given a yn star in the closure of the image by T star of the unit ball of X star, you pick your X star and in the unit ball close enough such that the T star Xn star is close enough to the Yn star. And then this gives that T star is a compact operator on capital X star.